Alright, I apologize again. The computer stopped recording video. I need to do a better job at keeping like the screen awake, even though I turned my screensaver off. Okay, so if you're continuing from the previous video, down here all I was doing was simplifying the derivative. All I did was, you do have the derivative on there, negative x minus 2 divided by x cubed. All I did was factor out the negative. Okay, so we found our horizontal asymptote, we found our vertical asymptote. Now we need to find the intervals of increasing and decreasing. So first we need to find our critical numbers. So take the derivative, set it equal to 0. Now, since this is a rational function, the denominator can never be 0. So the only spot we care about is when the numerator is equal to 0. So negative x plus 2 is equal to 0. And if you were to solve this, we get 0. Okay? So we have a critical number at x is equal to, or sorry, I put 0. It should be negative 2. Negative 2. However, we do have another critical number. That's why I wrote 0. I was thinking of the other critical number. We do have a critical number at 0. The reason why we have a critical number at 0 is because the derivative is not defined at 0. I can't plug 0 into this derivative and get back out a number. Okay? So those are our two critical numbers that we have. Okay, so let's see. Find the intervals of increasing and decreasing. So I'm going to make a number line. I'm going to put 0 on there. I'm going to put negative 2 on there. As you can see, it splits the line up into 3 intervals. We've got that blue interval there. We've got the red interval there. And then we've got the green interval right there. So we're going to pick test values. So test value that I'm going to pick from there is negative 3. Test value that I'm going to pick from there is negative 1. Test value I'm going to pick from there is 1. Now this one, we're going to care about the numerator and the denominator because when we plug negative numbers in the denominator, they're not always going to be positive. Sometimes they're going to be negative. So we got to be careful. So negative x plus 2 over x cubed greater than 0. So we're finding the intervals of increasing because we took the derivative and set it greater than 0. So now let's plug in our test values. So first test value, negative 3. So on the numerator, we've got a negative number. If I plug negative 3 into here, I get negative 3 plus 2, which is negative 1. That's a negative number. And then divided by negative 3 cubed, which is negative 27. That's also a negative number. Is this greater than 0? Well, a negative times a negative is a positive, so we got a positive on top. Positive divided by a negative is a negative, so a negative greater than 0. No, this is not true. So it is not increasing on this interval. So I'm going to put an X here. Not only that, I'm going to record the fact that it was a negative on that interval. So now let's do the next test value of negative 1. So I've got this beginning negative. If I plug negative 1 into here, negative 1 plus 2, that's a positive. Divided by negative 1 cubed is negative 1, so that's a negative. Is that greater than 0? Well, a negative divided by a negative is a positive. A positive times a positive is a positive. So I got a positive being greater than 0. Is a positive greater than 0? Yes. So that worked. And I'm also going to record the sign that we had. Now we got one more test value. Test value of 1. So plug 1 into there. We've got the beginning negative. We've got 1 plus 2, which is 3, which is positive. So that's a positive number. Divided by 1 cubed, is a positive number. Is that greater than 0? Well, no. This is going to turn out to be a negative. So this is not greater than 0, and I'm going to record the sign of that interval. Okay, so now we know that we are increasing on the intervals that worked from -2 to 0. -2 to 0. Let's see, we know we're decreasing from -infinity to -2. Also from 0 to infinity. Not only that, since we found the intervals of increasing and decreasing, and we also have our critical numbers, we can tell whether we have local mins or local maxes at those critical numbers. Now, we have to exclude 0 because 0 is an asymptote. So, we have a local, let's see, at -2, well, here's -2. This is why I recorded the signs of the interval. It went from negative to positive, and if you remember the first derivative test, going from negative to positive means we have a local minimum at x is equal to -2. Okay. So, now we need the intervals of concavity and the inflection points. So now I'm going to take the second derivative of this thing. Now it's in the form of a quotient, so I got to use the quotient rule. Let's see, the derivative of the top is just going to give me a -1 times the bottom, so -x cubed minus the top, which since it has a negative, it's going to turn to a positive x plus 2 times the derivative of the bottom, which is 3x squared, divided by x cubed, all of it being squared. Okay? So, let's go ahead and see what we get. If I were to distribute this piece here and here, we're going to get a 3x cubed plus 6x squared. And then we can combine some like terms. So on the numerator, we're going to get a 2x cubed plus 6x squared all over x to the 6th. Now, we can simplify this a little bit. Actually, let's not simplify it. No. Let's go ahead. X squared 2x plus 6 divided by x to the 6th. Well, x squared cancels with 2 of those, so we get 2x plus 6 divided by x to the 4th. So there is our second derivative. Okay? So we no longer need our first derivative. I'm going to write it up here. F double prime of x is equal to 2x plus 6 over x to the 4th. Okay, so let's find our inflection points. So that's saying take the derivative and set it equal to 0. So 2x plus 6 is equal to 0. Again, we have a rational function, so we don't care about the denominator here. The only way that this is going to be 0 is if the numerator is 0. And if we were to solve this, we find that we have an inflection point at x is equal to -3. So now what we're going to do with that inflection point, it's a lot like our critical numbers and the increasing-decreasing test. I'm going to take a number line. I'm going to put -3 on here, and I'm going to pick test values. test value of -4, test value of 0, just because I can't pick 0. 0 is a vertical asymptote, unfortunately. So let's go ahead and pick 1. There's nothing wrong with picking 1. So let's go ahead, test value, -4. Plug -4 into there. The denominator, since it's to the 4th power, it doesn't matter what number we plug into there, it's always going to be positive. So we don't have to worry about the denominator. We only have to worry about the numerator. So 2 times -4 plus 6, well, that equals -2. So the derivative at our of our test value is equal to -2, which is less than 0. When the second derivative is less than 0, you got a negative number, it means you're concave down. So we're concave down here. And if we do a test value of 1, 2 times 1 plus 6, well, that equals 8. So the second derivative at 1 is equal to 8, which is greater than 0. You're positive, so you're concave up. So let's write our final results. Let's right here. So concave down from -infinity to -3. Concave up from -3 to positive infinity. Okay, so that answers everything this problem was asking us to find. They first told us to find the vertical asymptotes, horizontal asymptotes. Here, set denominator equal to 0, solve of the original function. Take the limit as the original function goes to infinity, -infinity. Secondly, we took the first derivative, set it equal to 0 to find the critical numbers. Okay? The critical numbers are wherever the derivative is equal to 0, that's how we got -2. And where the derivative doesn't exist, that's where we got 0. To find the intervals of increasing, decreasing, we picked test values to look at the intervals. And then, based on the first derivative test, we were able to determine that we have a local min at -2. And then, lastly, we took the second derivative, set it equal to 0 to find the inflection points. And we used the inflection points, put them on a number line to test for concavity. Okay? Now, with all of that information, let's go ahead and make a rough sketch of the graph. Okay, so we've got a horizontal asymptote at 1. So right there's 1. Y is equal to 1. We have a vertical asymptote at x equals 0. We have a minimum value at -2, so -2 somewhere over here. C. Horizontal asymptote. Took care of this, took care of this. We'll do this. Okay, so let's see. Inflection point at -3. So somewhere over here at -3, we have an inflection point. Now, we're concave down from -infinity to -3. So, concave down here, we're concave up here. We have a local minimum at 2. So I want to put it down here. We're concave up here, concave up from -3 to positive infinity. We're always concave up. And then once we hit -3, we're going to start being concave down. So it's going to go towards our asymptote over here. As you can see, we are decreasing on the interval from -infinity to -2. We're going to be increasing on this interval from from -2 to infinity. There's a vertical asymptote here, so it goes up like that. Now the next part of the graph, we're concave up everywhere, from -3 to infinity. So we're concave up everywhere. we're also decreasing from 0 to infinity. So that's going to look something like that. Let's see. We got everything. Okay. Now, you should go ahead and try the problem that I have for you guys, the e to the x divided by 1 minus e to the x. And then again, check for my solution on Blackboard. And that's the end of 4.3.